Hi, everyone. Welcome to this edition of Project Pro's podcast on AI monetization, where we speak with industry AI leaders on the business outcomes delivered using ML and AI. Today, we have with us Patrick Bangert. Patrick is probably the authority on the application of AI ML to chemical, petrochemical, oil and gas industries. But Patrick started his journey writing machine learning code over 20 years back at NASA, figuring out the sun's magnetic field using machine learning way before it was all cool. During the same time, he worked at the Los Alamos lab, picked up a PhD in applied mathematics, and he started a company called Algorithmica, which did over 120 deployments for petrochemical, oil and gas industries focused on predictive maintenance. Following that, Patrick was a VP of AI at the Samsung Data Services, which is a $10 billion division of Samsung, where a lot of his work focused on life sciences and healthcare has been featured in a lot of publications. More recently, Patrick is VP of AI at Searce, which is a modern data and AI consulting company. And Patrick is also, recently included in the top 10 AI and big data leaders by the CIO Look magazine. Patrick, thank you so much for taking time to do this.
Thank you very much for having me, and thanks for the wonderful introduction.
Absolutely.
I now have to live up to it.
Well deserved. So, Patrick, it would be really helpful to begin with to understand in the petrochemical and oil and gas industries, what is different about the nature of these problems compared to the structure of these problems? What is different about them?
So the first thing to understand about oil and gas and petrochemicals, chemicals, is that it's a so-called asset-heavy industry, meaning that the majority of costs are related to machines and objects rather than people. So, most of the companies that, technology companies, software companies deal with are companies that are heavy on people, where the main costs are salaries and people and office buildings and things like that. The oil and gas industry is very different from that. And so most of the problems, AI problems and other problems in the oil and gas industry are physical. You have to transport stuff. It's a lot. You have to shift a lot of gear. That gear breaks all the time. The major expense in oil and gas is always maintenance. So you think, you're going to have to find a spot to drill, and then you have to drill a hole. All that stuff happens fairly quickly. But then that well, or that pipeline that you've laid might have to operate for 5 to 8 decades. Right? And it won't in the way that you've put it in place, right? So every once in a while, maybe, every few months or once a year, you're going to have to exchange some parts.
Yeah.
And, because of that physical work, most of the people on your workforce will be laboring with physical things, right? And so they're exposed to various physical hazards. We sitting at a desk, right? We're probably mostly at the risk of having lower back pain from sitting in a chair. But people who are out in the field, putting up a drilling rig or installing a gas turbine that's the size of your house, they will be exposed to real dangers. So obviously, predictive maintenance, to figure out when things are going to fail in the near future, health and safety of all of those workers that are in the field, scheduling, trucks and ships and things into the field. Those are all top of mind use cases in this kind of industry where, as I said, the focus is on stuff rather than people.
Yeah, that makes sense. Yeah, that distinction actually provides a lot of clarity on how the problems are different. And that leads me to a follow-up question, which is, when we speak to even companies where the assets are digital in nature, the problem is always getting the right data out of the digital assets. How do you manage that in non-digital assets that are like all, most of it below the ground and things like that?
Yeah. So, in the early 1990s, thereabouts, there was an innovation of something called a process control system. Basically, the idea is that processes, physical processes, where things move, mainly liquids, right? So oil is a liquid, gas is it's also a liquid in a sense. It's a fluid, even though it's gaseous, right? These are processes that are controlled by a variety of mechanical elements like valves that have to be opened and turbines that have to move stuff. All of this was controlled by people. And that presented quite a few dangers. So in the mid 1990s, a process control system was developed, which was initially also a little bit mechanical and then became more and more digitized through the late 1990s. So what you now have is you have a control room, an actual room in the plant where a few people sit, only a handful, maybe 5 or 6 individuals. And through the computer, they control a very large asset, like a chemical plant, right? Which could be a square mile in size. And you do that through having a very large number of sensors and actuators installed across the board. So you might have, in a typical industrial plant, you might have 1 or 200,000 sensors throughout the plant, right? Measuring temperatures, pressures, flow rates, rotation rates, vibrations, all sorts of things of that nature. So you might easily have 10,000 temperature sensors, right, throughout the plant. You might have a few thousand vibrations and couple 10,000 pressure sensors, things like that, right? So a lot of information is coming in, and this stuff is being retrieved at a fairly fast rate. So you might be measuring temperatures and pressures every second, flows every tenth of a second. Vibrations would be measured at 10 hertz or more. So the flow of information is quite fast. And all of this is being stored in central databases, process control systems that then automatically respond. So there are safety limits where alarms are released. There are automatic pre-programmed reactions to things, like if a certain thing happens, you close all the valves, right, to prevent a fire or something. And that's a fully digitized system nowadays. And for us machine learning AI people, what's beautiful is that you can go back 15 years, right? You can go to the database and download the plant's activities on fractions of a second level for the last decade or more. And thereby you get a very accurate fingerprint of the physics and the chemistry that has happened there over a long period of time. Including, and this is the really critical part, including all the stuff that went wrong. Right. So for those of us who want to do things like predictive maintenance, all of the maintenance activities are implicitly included in that database, right? All the failures are included in that database. And of course, all the normal operations also. So now you can learn to differentiate normal from abnormal, abnormal of type A from abnormal of type B. And you can learn all of this with machine learning, and therefore now you can do things like make a forecast or make an identification. It is of type B rather than type A. And then based on your standard operating procedures, you can then automatically decide what needs to be done. You hook that up with other systems, such as your storage systems of where the spare parts are, which spare parts you have on record, your employment system that tells you which people have what kind of certificates, right? for example, if welding needs to be done, the employee doing it needs to have a welding certificate, right? So that making sure that they have the expertise to perform that work. So hooking up all of those systems then allows you to immediately schedule a maintenance activity with the right people at the right time, in the right place. The right place, by the way, is also critical because we're talking about physically distributed assets, right? So transportation is always an issue, which means now you're scheduling trucks and all of that, right? So suddenly the whole thing is a spider web of various technologies that are integrated into a holistic whole, which ultimately generate a little pop-up window that says person A is going to take truck B to site C at a certain time with certain spare parts and certain repair equipment to do a certain task in advance of the failure that would have happened 2 days after that if you did nothing. Right? But generating that message, very complex.
Right. Makes sense. So it's very interesting. So you're basically saying there's literally a DNA footprint of the system going back at any slice of time you would like to. Literally. Okay. Very, very interesting. And inside a large oil and gas company, who is the person who kind of oversees this specific problem? Is it the data science team? Is it the business team? Or where is the stakeholder for a problem like this?
Yeah, that's a very, very good question. And of course, as always, with any other kind of company, there is no one stakeholder. There are always multiple stakeholders here. So generally with predictive maintenance, it is the head of maintenance that is going to be the executor, let's say, of it, because that individual and their department will have the people who are actually going to do things about this. They're the recipients of that message that I talked about. They will drive out to the field. They're the ones who have the storage facility with the spare parts and the equipment and all that. In most companies, though, maintenance is a cost center. So, of course, finance will be involved. And finance's interest in doing AI projects is, of course, for us to lower the maintenance cost. So there is a little conflict of interest in the sense that maintenance wants to do good maintenance, but they don't necessarily want their budgets cut. Finance wants to cut the budgets, and AI is supposed to enable that, right? So now the AI department, if there is such a thing, is caught a little bit in between. And of course, you have a plant director who is responsible for everything. You have an operations director who doesn't want downtime, and therefore is again caught between two rocks in a hard place, because on the one hand, maintenance has to be performed for the plant not to have much downtime, but every maintenance activity is downtime. So you have multiple conflicting interests here, both physical interests like downtime with financial interests, and of course the people themselves are heavily interested in their own safety. So multiple conflicts arise, and so multiple stakeholders are involved in the process, and us AI people then find ourselves being a very cross-functional team that is a horizontal across the whole organization.
Now, with the problem that you mentioned, right? I mean, it sounds mission critical, and it sounds as if the ROI on this is very clear. Is that the case, or is that not really the case? It's more of a gray area.
It is certainly mission critical in the sense that all of these activities I describe are mission critical. And there certainly is a very sharp dividing line. If the failure event happens, it happens in an instant. If you shut the equipment down just minutes prior to that, or minutes after that, the differences are dramatic. I mean, the equipment's broken one way or the other, but there's collateral damage if you let it fail, and there's no collateral damage if you stop it prior to failure. right? So that difference is very sharp. And typically we see that the cost of repair is more than double if the failure event actually happens. So the collateral damage is typically larger than the original damage. Plus, some of the collateral damage is related to people, right? So people get injured in failure events.
Right.
So it's certainly mission critical. Now, the ROI, however, is not always very clear. And that's kind of the tricky part here. So on the one hand, AI makes mistakes, right? Every AI model is only statistically accurate to a certain degree, which means it does and will certainly make errors, and that's built into AI. And that's always a very difficult thing to reconcile for physical industries, where these events are expensive. So it's obviously very expensive for me to let something fail, but it is also expensive for me to stop, open up, and investigate a system that is actually fine.
Correct.
So here's the next dilemma, right? The AI gives me an alarm. Is it genuine? Right? I'm not sure until I check, but checking is expensive. And checking is also risky. Or if the failure event is going to happen and I can see that, is it going to happen at the time that AI tells me, right? If AI tells me I have 10 days and now I schedule a repair activity on day 8, is that enough? I cannot be certain of that. It could be that the system will fail on day 7 and everything is obsolete.
Right.
There's always a risk of these things. And so the ROI, unfortunately, is a statistical ROI, and the stakeholders are going to have to be okay with that. Now, human nature is not to be okay with that.
Right. Especially on the business side, I guess.
Yes.
Yes. Yeah. That makes a lot of sense. That's very well said. Going like one level towards a technical domain, Patrick, I assume the hundreds of thousands of sensors that you're talking about have been put in there for a while right now. As the algorithms go from statistics to data science to machine learning, those sensors have been there for a while. So, and the data has been roughly the same. What has really changed? Is it very clear to say until this point, it was more data science problems. Now these 3 machine learning algorithms came up. Now, these are machine learning problems. Is there such a graduation that you've seen over the decade?
No, because things like data science and machine learning are not competitors or steps on a ladder. They're steps in the process. They're all necessary simultaneously. So the physical systems of sensors and databases that are in place are merely there to obtain the data and store it somewhere. But like every data scientist, machine learner will tell you, data first needs to be cleansed before you do anything with it. And that is the primary effort, right? In an AI project, 80% of the manual work, the human work involved is cleaning the data. So if you have an expansive system of sensors, some of those sensors will malfunction. They will record some wrong values. There will be connectivity issues where no values are recorded for a period of time. It could be a short period of time, but it will be there, right? So you have to deal with all the usual stuff: missing data, wrong data, drifting sensors, all sorts of issues. So data cleansing is a definitive problem. Then for certain types of questions asked by machine learning, you will want to exclude or include certain types of data. Those decisions have to be made by people, but then they have to be executed by those people too. And so that takes time. So there's data cleansing, which is a big part. And then there's data science. Data science will do things like identify the right variables. So let's say I want to forecast a certain vibration, because if it vibrates too much, it explodes. What variables are informative to do that, to forecast this? not all tens of thousands around the plant clearly. So there is a subset. How do I find that subset? That's a very tricky question. And it's partly a question to people who know their stuff, and it's partly a question to the data. So that's a data science question. Then can I somehow transform my data set to be a different data set that is more informative? So for example, based on physics and engineering, I might know that the ratio of A divided by B is somehow much more informative than A and B separately. Okay. Discovering that very simple fact might be hours of conversation with physicists and engineers and so on that are working for the company, right? Then I leave, a couple of days later with the insight that, I have to create a synthetic sensor that is A divided by B. And somehow that gets me a step forward, right?
Yeah.
So I do that.
Mm-hmm.
Great. So I've created my 200,001st sensor, which is a calculation sensor, which I add. And then I can remove A and B from the list of independent variables and add this new one, right? So all of that is intellectual work. It is collaborative teamwork that happens in rooms. Yeah. That's data science. Mm-hmm. But so this particular activity is called feature engineering, which is absolutely crucial in the process. And then once I've done all of that data science, figured out all of it, then I can do machine learning, machine learning at that point then is actually a fairly simple activity because I've completely prepared my data by this point. I know exactly what the independent and dependent variables are. Mm-hmm. Now the only thing left to choose, and it's not a triviality, but it's easier, is what type of model am I going to use? Right. Do I use a random forest, a support vector machine, a neural network, a LSTM, recurrent neural network, whatever, right? Which choice do I make? Mm-hmm. Once I make that choice, there are several that are called hyperparameters that I have to choose next. Mm-hmm. Right. So how many layers, how many neurons per layer, how many trees in my random forest will I allow, right? What kind of pruning ratio am I going to have in my forest of trees, et cetera, et cetera? Yeah. These are choices that I have to make. And unfortunately, at this point in time, the holy grail of all of machine learning and AI is how to tune the hyperparameters automatically. Mm-hmm. Spoiler alert, nobody knows. Mm-hmm. So the only way, by the way, if anybody out there ever discovers how to tune hyperparameters automatically without brute force, they're probably going to win a major Turing award. At the moment, the only way we know how to do this is brute forcing it. Basically trying as many options as we can and picking the best one. All right. But it's worth it because that leads to good results. Mm-hmm. And that would be the major machine learning effort. And then once you've discovered the right type of model and the right set of hyperparameters, then you just train them all, and there you go. Right? But all of these activities are complementary to each other.
Right. That makes a lot of sense. Very well explained, the whole end-to-end pipeline that's needed to get this done. So like you said earlier, in this world where deterministic outcomes have material impact on people and real machinery out there, right? Where does Gen AI with its whole stochastic outcomes fit in, or does it fit in at all to solve problems?
In the kind of scenario that I've been talking about here, where we're really talking about numerical time series, Gen AI doesn't fit in any way at all. So that, by the way, is one of the important things to realize about generative AI or large language models, right? They're not a panacea for every type of problem. They're fantastic at what they do, and they cannot be used on other things. So they're models of language, which is fantastic in other areas of the company. So, for example, if you're looking at the legal department and you want to look at a vast array of contracts that you have and discover certain things, like you want to find the contract that doesn't have a termination clause. You want to find the contracts that have a critical date in the next month or quarter, right? Gen AI will read them all and pop them up. Boom, there you are. Would have taken an analyst weeks to do that. It takes Gen AI seconds to do that. Fantastic. If you want to look through the finance department and surface all the invoices for services that were not actually performed, right? Fraudulent stuff. It will do that again in seconds, right? Beautiful for that. Very important for the oil and gas industry, by the way, because it works with a large variety of small vendors, and so gets a great many invoices for all sorts of small activities, and stuff falls through the cracks all the time, right? So doing fraud on invoices is an important activity. Notes is another thing. So when you have people in the field, they ought to take notes on what they do. That's tricky, right? If your hands are covered in oil and you're holding onto a pipeline, taking notes is kind of hard. So if you can do that with your voice, right, and then use Gen AI to transcribe your voice into a writing note style, that's helpful. You can use other types of AI, for example, in glasses that allow you a heads-up display in your goggles, right? To superimpose on your vision certain types of maintenance manuals or instructions, or if you have to ask for help, from somebody in who's somewhere else, right? To help you out through the visual interface. Things of that nature can be quite helpful as collaborative tools. But you need to use each tool in its own track. Right. So anything language relevant, of course, LLMs are great.
Makes sense. Once you've identified the problem, the right model, you have a POC working, the tech stack that's needed to take and deploy the model and take it live, is that similar to what one would find in other industries, or are there key differences on the tools used?
The tech stack would be about the same. Again, it depends a little bit on the use case itself. So again, if we go back to that numerical time series example I brought earlier, the kind of time criticality of it might be a little different. So this really needs to have an uptime of 24/7. It needs to be very responsive. So it needs to. Some of the systems will need to respond in a small fraction of a second. So, for instance, LLMs are a bit slow for that. You can't make an LLM react in 50 milliseconds typically. So using it for those kinds of processes is not only the wrong thing conceptually, it's the wrong thing infrastructurally as well. So you need to keep some of those requirements in mind and in line. But other than things of that time-wise nature, I think the pipelines would be about the same. Of course, the thing to mention is that there is a critical difference of models that you've created yourself and models that other people have created for you, right? So if you are generating machine learning models yourself based on your own data, then you will have to also yourself do the operations, which means that those models will become obsolete after some period of time, and it's usually faster than you think. So, for example, in the retail industry, we retrain the models every week because they become obsolete at the end of the week. It's very fast.
Okay.
So the level of observability that you have to perform on a regular basis, collecting more data, cleaning that data in perpetuity as you go on, so that you can perform a retraining activity. And in physical plants, you might want to do that every 2 to 3 months, right? So every quarter, basically, right? What
Yeah.
you want to do is you want to go through a cleaning exercise for that quarter's data
Mm-hmm.
and then perform an incremental training step on
Mm-hmm.
all of your machine learning models and redeploy them all.
Mm-hmm.
If you're the customer of an LLM service, then of course you don't need to do that. Your LLM vendor will take care of it for you. And yes, you better believe they're doing it.
Right.
But you don't have to worry about it.
Right.
But if you're generating the models, you do have to worry about that. So just keep in the back of your mind as well that models are not static.
Mm-hmm.
Models are themselves an evolving entity. And if you've done something that presumes the model as static, which for LLMs would be prompt engineering, for example, that has to evolve as well. So if you're currently doing a prompt engineering exercise for a ChatGPT or a Llama, something,
Yeah.
then as they come up with their new versions every few months, you will have to recheck whether that prompt engineering is still valid or not.
Right.
And better believe it, at some point it will cease to be valid and you will have to redo that prompt engineering exercise. Because it has to evolve together with the model.
Right. That it makes a lot of sense. I guess the key difference between a typical regular computer program and a machine learning model, it's not just build once and forget it. You're constantly incrementally making it better. Um, as an entrepreneur, Patrick, I'm also curious. What was the insight that kind of led you to founding Algorithmica early on, and how was that journey?
Yeah, so I mean, I started as an AI expert back in 2005, deciding to create my own company. So this is prior to deep learning, prior to all of the hype that we see nowadays.
Yeah.
AI was a bit under the radar. We had come out of the winter, but it was early spring, let's say, in that analogy. I was in Germany at the time, and I tried to meet with as many companies as I could to say, hey, I have AI and I'm looking for a problem to attack with it. And I found the petrochemicals industry had a problem that was consistent across all the companies I met from that industry. Everybody told me about two problems: predictive maintenance on the one hand and process optimization on the other. Basically, the processes have certain what they call set points. Basically, for each one of these measurements that I've described, there is a certain goal value, right? The optimal temperature is this one. The optimal pressure is that one. And of course, due to the world happening, like nights are colder than days and so on, the temperatures are never quite perfect. And so you have to adjust the process to match. So calculating, though, what the optimal values are is a tricky thing. And so that's process optimization. So those two problems were posed to me by every one of the petrochemical companies I talked to. And then I thought to myself, okay, there's a pattern here. There's obviously a niche for this market. It's an unsolved problem at this time. It's solved now, but it was unsolved at the time. It was done by people. And so that's what I'm going to pick as my niche. I'm confident I can solve this problem scientifically. I'm confident that I have a small number of well-funded, large potential customers, right? Which is something you have to watch out for. And so that was, I think, a good approach. You have to see that on the one hand you can do whatever it is, and on the other that there's a market for you that's actually willing to pay you, that's able to pay you, and the market has certain characteristics that allow you to actually address it. So personally, I've never had any kind of product that faces the general public, like a kind of retail thing. So I don't understand how the retail market works, right? How you sell something to millions of people, I don't know. Other people might know how to do that. To me, it's daunting. I know how to sell stuff to 10 people. And that's again what the oil and gas industry allows you to do, right? To have a very deep relationship with a small number of customers, and
Right.
that's just fine and just enough to have a well-running business.
Right. Okay. Yeah. I mean, 10 very well funded, large, customers, right? I mean, that's a skill by itself, getting them and most importantly, retaining them. So, and again, with my limited knowledge of the oil and gas industry, Patrick, uh, where does a company like, for example, C3.ai fit in, in industry like that? Is that a product or a service or a combination of both? Do they operate in the predictive maintenance space?
Yeah, so there are a number of other companies, software companies,
Okay.
that have, been in this field for longer than me,
Hmm.
for sure. And there are many new entrants as well that are trying to activate the C3 AI is an example.
I see.
And they, in particular, have, in my opinion, had an identity crisis ever since they got started
Hmm.
on what exactly they want to be, and I don't think they're sure up to today even.
Hmm. Hmm.
Um, they wanted to be services for a while. They had a product for a while. They wanted to be a platform for a while.
I see.
Um, so I'm still a bit confused on what exactly they are.
Yeah. Got it.
And it's difficult because, of course, again, you're trying to sell to large companies and to a small number of them, and you're trying to be repeatable, and that's difficult.
Got it. And just, finally, as you look out kind of into the future of AI/ML in Gen AI, sorry, in oil and gas, uh, do you see an entirely new category of problems that will get solved? Or do you see the current problems with a huge delta improvement in outcomes? What do you see as you kind of look forward?
Yeah. So the primary danger that I've seen over the industry of oil and gas and petrochemicals is that um, the leadership has been very interested in AI,
Hmm.
but very cautious. That's led to a very large number of POCs being done. So if you look out on the internet or in journals or in conferences, you see a vast number of POCs, research studies, papers published, studies published, um, and hardly any of them have made it to productive use. So that's really the problem
Hmm.
in the industry, is that scientists and startup companies are stuck in what they call the pilot purgatory, um, of where you're constantly trying to prove something and it's never quite up to the mark. And that's because the standards don't line up. Generally, the oil and gas industry comes from a physical engineering perspective,
Yeah.
um, of where you kind of over engineer, right? If you calculate that the thickness of something has to be 1 inch, you just make it 2 inches and you're good to go. And then it might be more expensive and more heavy, but it is always going to be stable.
Hmm.
Now, the problem is with AI, there is no analogy of doing that. It doesn't exist. You cannot make AI twice the thickness and therefore it will always work. It's just not possible. And so once those mindsets come together in one room,
Hmm.
the physical engineering perspective is you failed.
Right.
And the AI perspective is we made it to 99% accuracy. This is
Right.
absolutely fantastic.
Right.
Right.
Yeah.
And the engineer said, well, you failed.
Yeah.
Right. And this is where pilot purgatory kills everyone.
Hmm.
So there has to be a kind of mindset shift on both fronts, where they can come together on some sort of common ground and agree that, statistically speaking, this is very helpful. But there will be painful incidents where AI will fail, and we have to be okay with that. So that, I think, is kind of the critical boundary here, where those two worlds have to somehow meet, so that all of these POCs can get across the hurdle. The second, slightly more minor issue is that I think a lot of people, not just in oil and gas, I think a lot of people just outside AI assume that AI is automatic. And because it's automatic and intelligent and software, it is two things. It is instantaneous. You can do this next week, right? I mean, it's AI, right? Just turn it on.
Right.
And two, because you can do it next week and you just have to turn it on, it's cheap, right?
Mm-hmm. Mm-hmm.
Well, no, neither one is true, right?
Right.
You require a lot of people who are expert in AI and who are expert in your domain, and those are not the same people, by the way. They cannot be, right? So it's necessarily a teamwork effort to put this together, and that team will require time, and that team is going to require funding. So it is not fast, it is not cheap, and you're going to have to pay attention to it for a while. And if you don't have the budget in time and money and the attention span to see it through, then again, it'll lead to failure. And that's the second big kind of mindset shift that has to happen. And of course, the AI industry is not doing itself any favors by the current hype that it's going through, right? All the major cloud providers are saying, yeah, we can deliver these use cases in like one day. And well, it's just a lie. They cannot, right? They can do a fancy show and tell in a day, but actually delivering a productive, useful pipeline, they also can't, right? And so the customers have to realize that those are the two big obstacles that I see.
Right. That is actually very well said. This whole mindset of versioning and experimentation that exists on the AI side versus you build once it's got to work on the physical asset side. It's got to be some way to bridge that gap. So on that note, Patrick, thank you so much. This has been fantastically helpful. Really appreciate the time you took to do this.
Thank you very much for having me. It's been a pleasure talking with you.